Hello everyone and welcome on today's video. My name is Wouter Pere. I'm the founder and main developer of GHEtool Cloud, and today we will be talking about the Separatus heat exchanger and more specifically the model behind it. So as if you might have read on our website, with GHEtool we really want to be a catalyst for geothermal innovations, and that's why we are open source based. We are working together with research institutes, with university, but also with industry partners that have developed innovations of their own, and we try to work together with them to develop a model which we can implement into GHEtool and which you as an end user can also use to calculate with the newest and latest innovations from the industry. And this is what we did with our partner Separatus. So if you're not familiar with Separatus, it's a Swiss invention developed in 2023 by Dietmar Alger, Jana Walker and Stefan Geese. And it's based on what they call the split pipe technology. So what they did is they took a circular pipe, traditional circular pipe with a diameter of 51 millimeters, and they installed a membrane, a separator, let's say, in the middle to separate the cold from the hot liquids. And the philosophy on this system is that you only have to install a single pipe in the borehole instead of two for the two legs of the single U-tube, or even four for the double U-tube in the ground. And this reduces your installation time quite a lot because it's easier to let down one pipe instead of two or four, but you also have half the amount of couplings, half the weldings. You can also decrease your borehole diameter since you do not need that much space in the ground, and taking all these factors into account, you should end up with a system which is more economically viable due to a lower investment cost. Now, developing a model for any type of innovation is not that straightforward, since there are different complexities that you can take into account. Now, Separatus decided on a more engineering-based approach. So what they did is they took a look at the equations which are already out there, and they said, well, our system more or less looks like a single U-tube, or is best represented by a single U-tube, but we're going to tune the parameters of the single U-tube based on real-life measurements. And this calibrated model, let's say, is then implemented in GHEtool. Now, these measurements are not lab measurements. It was based on a real-life project. Let's call it the experiment, which was in Altach in Austria. There were 3 boreholes drilled of 70 meters deep, and one of them was with a double U-tube and another one was with Separatus. They installed extra valves in the manifold in order to be able to select, to guide the flow rate to a particular borehole. So to really play around with which heat exchanger the heat pump is interacting. And they did 2 measurements, one with an equal flow rate and one with an equal heat transfer rate. And based on this equal heat transfer rate, they were able to reverse engineer the parameters of the single U-tube, which best represented the Separatus case. So let's go over these measurements. So the first experiment was with an equal flow measurement. So what they did is they they installed the valves, or they put the valves in such a position that both the double U-tube and the Separatus had a flow rate of 1,100 liters per hour, and they did that for over 90 hours, which you can see is the time frame below. And then they looked at the longest continuous runtime of the heat pump, which is actually the one in close-up here. Now the figure is in German, but what you can see is that the yellow and the green line are for the Leistung, which is the heat extraction, it's the power for both Separatus and the double U-tube. And the other ones are the fluid inlet temperature. Now, as you can see, we're more or less steady state because the power, the heat extraction is more or less constant. And what you can see is that the GHEtool has a higher heat extraction rate from the ground than the Separatus one. Now, since we're looking at the short-term effects, only a couple of hours, we can say that the ground temperature is more or less constant. Now, if you're not familiar with this distinction between long and short-term effects, please take a look at our previous videos in the video description below where we talk more about that. But since we're only short-term, we can say that the power, the heat extraction rate, is inversely proportional to the borehole thermal resistance. So what we then can do is that we say, well, let's assume that the GHEtool has an effective borehole thermal resistance of 0.12 meters per watt, meter Kelvin per watt. Then we know that the Separatus is 0.156 due to the ratio between the powers which were measured with our system. So this was the first measurement. Now, in order to be able to really calculate the parameters or to really calibrate our model, what we want is actually a measurement where both the power from the GHEtool and the power from the Separatus heat exchanger are the same. So that's why the second measurement, which is called the equal heat transfer measurement, is where we fine-tuned the flow rate in such a way that both the W Leistung or the GHEtool power and the one from Separatus, they coincide. They are almost exactly the same. And this is when we have a flow rate through the GHEtool of 550 liters per hour, which is the laminar range, which is typical for a GHEtool, and 1400 liters per hour for Separatus, which is in the transient range. So we have a higher Reynolds number and a better heat transfer there. And as you can see, then the powers are more or less the same. Now, if we do so, we know since Separatus and GHEtool have the same borehole effective resistance, we can use GHEtool or Earth Energy Designer to calculate the parameters or we can use the model with the GHEtool in order to calculate the borehole effective thermal resistance. And given that number, we can reverse engineer what parameters we should take for the single GHEtool in order to come up with the same effective resistance. And this is what they did at Separatus. So the model which is implemented into GHEtool has a pipe diameter of 35.74 millimeters. Now, this is perhaps a rather random number, but it's based on the hydraulic diameter. So within the domain of fluid dynamics, most correlations are for circular pipes, but there are also rectangular pipes or split pipes, etc. And in order to use the traditional correlations for circular pipes, they typically work with something called the hydraulic diameter. So this is taking into account the circumference of your actual pipe and the surface area, and taking those two parameters into account, they can come up with a diameter for a circular pipe which has the same fluid dynamic properties. So if you take into account the geometry of the Separatus heat exchanger, you calculate its hydraulic diameter, you end up with a circular pipe of 35.74 millimeters. And with the wall thickness of 3, which was the real wall thickness of the heat exchanger. And then we have two more parameters which were determined by trial and error. So the pipe to center distance, or the shank spacing, if you're familiar with Earth Energy Designer, was found to be 18 millimeters. And we also added another contact resistance of 0.03 meters Kelvin per watt. Now this contact resistance, if you recall our discussion on the short-term effects. There we had a fluid pipe resistance, resistance through the pipe, and a pipe grout resistance. Well, we here added another contact resistance. And this is in order to take into account the thermal interaction between the cold and the hot leg, which are only separated by this separative, this membrane in the middle of the pipe. And this is also found by trial and error, and 0.03 meter Kelvin per watt was found to be rather well in line with the measurements. So this is actually the model which is implemented into GHEtool, and we adapted this extra, or we added this extra resistance to the short-term effects. Now, of course, this is not a final model. So currently there are some simplifications Separatus did. It's namely, as we discussed, it's not based on the real geometry. So it's not the Separatus probe itself that it's modeled, but it's based on an approximation. So it's based on a single U-tube, where we did some parameter fitting, we did calibration, but the calibration was only based on one initial measurement. And because it's a rather new product, there was only one case, one experiment that could be done. So we can say that the model is reliable, but mostly under the same circumstances or the same conditions as in which the measurement took place. And this is specifically when you're working with the transient flow regime for your Separatus heat exchanger. So for future model updates, we're actually working together with Separatus to create really a model that's based on the actual geometry. So where we can actually model the heat transfer through the membrane between the hot and the cold leg, but also take better into account the heat transfer to the borehole wall. And since there are now more projects done with Separatus in practice, we will also have more data to work with and to calibrate this model. And this is a collaboration between INEAT, the company behind GHEtool Cloud, and Separatus. So I hope you'll find this video interesting and you better understand how the model of Separatus came to be. If you think this is interesting, please consider subscribing, sharing this with your colleagues. Try it out yourself, try calculating something with the Separatus heat exchanger if you're curious. And in a couple of weeks, we will do a webinar together with Separatus where they will tell you the advantages of their system. They will also talk more about some case studies they did, some practical experiences. And we will go over how you can design now your system in practice with using GHEtool Cloud. So follow us on LinkedIn if you do not want to miss that, and we see each other in the next video. Take care. Bye.